Good morning, everybody. It's a pleasure to have you all here. Welcome to the webinar organized by Zemgala Regional Energy Agency from Latvia and Biogas Oslofjord from Norway within the INTERREG Baltic Sea Region Program project BREC, bridging the gap between research and education for the circular bioeconomy. And this project will tackle the challenge of going from linear agriculture economy to circular bioeconomy, the challenge of teaching and spreading new knowledge. My name is Gundars Reders. I'll be serving as your moderator today. And Inga, my co-host. Hello, Selma, Amalie. Hello, good morning. How are you? This is our last of our 3 webinars. How do you feel about it?
We are excited to hear new knowledge again.
Okay, it's a pleasure to hear. So yeah, this webinar also will be recorded, so you can come back to this knowledge afterwards. Your questions, remarks, comments are welcome. After each presentation, there will be 10 minutes time for questions. So you can write your questions in the chat room. And you can raise your virtual hand, and unmute yourself and speak out for questions, of course, but we have to consider limitations of our time frame. As first, I would like to give the floor to Mats Edström, agricultural biorefinery concept. Mats has worked for about 30 years with applied research in the field of biogas. He has also worked with biorefinery concepts based on biomass from agriculture. So welcome, Mats. The stage is yours.
Thank you. Okay, so the presentation will be, the title should really be biogas-based agriculture biorefineries, I guess. Anyway, we can take the next picture. So I come from a Sweden research institute called RISE, and we are a state-owned company with approximately 3,300 employees. We are really a fusion of several companies, institutes that come into the frame of RISE. I think it's some 20 institutes or something. So we work with our customers and partners to develop competitive solutions that drive sustainable development forward. You could say that's one thing that is important for us. We have a lot of test beds in our institute. Says about 130. I'm working with a couple of them. My background is that I'm an engineer, and I like to make a lot of calculation around the biogas system, you could say, and works a lot with mass and energy balances. So you will see some part of that in my presentation. We can take the next. So here is one example of test bed that that I have been working with, and we have focused on making better fertilizer product out of digestate. So this test bed is located at an agriculture cooperative biogas plant called More Biogas plant. And we have a lot of basic equipment here, like separators, where we can separate the digestate in different kind of fractions to maybe get the fertilizer fraction with higher phosphorus content and so on. But we also have worked with several other concepts to improve the fertilizer. So for instance, we have also tested and applied nitrogen enrichment unit that Trond Lund presented, I think it was the last presentation round. So we tested for a couple of months with big estate at this biogas plant. Okay, next page. So we have been working with a case around agriculture biorefinery in a certain region in Sweden called VGR region. So that region is in the southwest of Sweden, the main city in that region is Gothenburg, and the second largest of Sweden, of the cities of Sweden. You see the border of BREC region marked in the larger, in the one of the maps here, and there you also have colored part of the areas. I come back to what that color means. And what we have been focused on is to show how the agriculture can be more self-sufficient and independent of fossil energy with this agriculture biorefinery concept. Next page, please. So a short description of the agriculture in the VGR region. So it's close to 20% of the Swedish agriculture is found in this region. There is some 250,000 cattle, a little bit more than 300,000 pigs, 3 million poultry, and 88,000 horses. We have got quite a lot of horses in Sweden. Anyway, manure from those animals is included in this concept, where part of it is supposed to be digested. Then it's about 520,000 hectares of arable land, that about 200,000 is used for cereal production, and another 200,000 for lay and green fodder production, including maize. There is also some 28,000 hectares of fallow in the region. Residue streams from this production is also used in the calculations. The agriculture use a lot of production means. So example of that is imported protein feed, 26,000 tons per year, and approximately 84% of that is soy protein, and is used for pigs and poultry mainly. There's also the agriculture also use approximately 40,000 tons of nitrogen and 4,000 tons of phosphorus mineral fertilizers. And the nitrogen is produced by natural gas, and the need of natural gas for that production will be around 400 gigawatt hour per year. And then the tractors and harvesters needs fuels, and that is close to 400,000 gigawatt hour per year, 374 more exactly, and then additional 39 gigawatts hour for oil for drying cereals and oilseed. And finally, there is biogas production today in this region, and that is about they produce about 300 gigawatt hour biogas there right now from approximately 45 biogas plants. Next slide, please. The agriculture biorefinery concept has been developed by a case study for the VGR region, and it's based on residual streams from crop production and animal production, and also together with cultivation of nitrogen fixing lay for a sustainable crop cultivation that combines a little more like farm close processes such as biogas production and protein extraction with maybe extremely large scale processes such as the bee oil production. We have been calculating the degree of self-sufficiency for the agriculture with regard of fuels to tractors, so on, protein feed, and nitrogen fertilizer. And that is the extractions process that use locally available biomasses like ELOC-free biomasses. Then it's no conflict concerning the production of food versus energy. And we also have made a cost assessment for this. We have also been calculating a biomass potential in the region, but also the potential production of biogas and bio-oil from HTL plants, and that stands for hydrothermal liquefaction that generate a crude oil. And that technology is it's a high temperature and high pressure concept, mainly it's under development, you could say, and it's mainly focused on used with biomasses from the forestry. But the biomasses from the agriculture can also have similar properties. So maybe it can also be used, the hotel process may also be used for some of the biomasses generated from the agriculture. But we have been looking on that to use this type of processes for fibers that is not degraded in the after digestion. We have assumed a cooperation between farms with different production, like crop production or livestock production, and that for more efficient utilization of plant nutrients, and also to reduce the dependence on fossil energy, and a more higher variation of crop rotation. I want to show that the crop rotation needs to be modified in order to maintain the fertility of arable land, so we don't lose carbon. So we keep the carbon level in the fields, although biomass is delivered to this biorefinery. Next page, please. So a little bit of the feedstock composition that is assumed to be treated in the biorefinery. So about the potential, we have calculated potential biomass in the region, and we use approximately 30% in our calculation. We need approximately 30% of the total potential of manure, some 20% of the straw potential we have calculated, and about 30% of the possibility to grow ley for the biorefinery. And in the feedstock composition, the contribution to the methane production is approximately 50% from the ley, and that could be both from the press cake generated after during protein extraction from ley, but also some ley is put directly into the digester without any protein extraction. The straw contributes with approximately 10% of the biogas production, manure about 20% of the biogas production, and then we also assume that the biogas plant is also digesting some smaller amount of organic waste. Could be waste from food industry or that kind of waste. The next page, please. So this is an example of mass and energy balances I have done for this system. I will not go into the figures, but in generally you can say that this is a smaller plant we have been calculating two different kind of plants, and this is a smaller one. And then the smaller one lay crop and side lay is used for protein extraction, and then you generate a pressed juice, and that is used for pigs, feed for pigs. And there have been a presentation before in this webinar series from Aarhus. Andrade was holding that, I think. Then the biomass I described before is then entering the digestion process, generating 60 gigawatt-hour of biogas per year. And from the digger state, there's first two separation steps. The first separation step is separating mostly fiber phase, and that is assumed to be transported away to a big hotel plant. And maybe it's not more than just one of these hotel plants in the whole BREC region. And that plant is also assumed to maybe use biomass from the forestry together with biomass from biogas plants, or extracted the fibers from the digger state more exactly for production of crude oil that then could be upgraded to vehicle fuel quality. The liquid fraction from the screw separator then goes to a centrifuge, and then you will have two separate fractions, a solid fraction and a liquid fraction. And the liquid fraction goes back to the farmers that deliver liquid manure to the biogas plant, and the solid fraction goes to the farmers that cultivate ley to this system biorefinery. And then they will get back a more phosphorus-rich fraction, and then they will get a more phosphorus-rich fraction as a fertilizer. Next page. So this is the larger plant and that we have been used for the calculations. It's produced about 100 gigawatt-hour of biogas per year, and it generates a protein concentrate. That's the main difference, really, that in this case, you press raw ley, not enzyme ley, but raw ley, directly harvested ley. And then it's possible to produce a protein concentrate instead of a liquid protein feed when you use enzyme ley. Otherwise, it's quite similar to the little bit smaller plant I described before. The number of smaller plants, assumed number of small plants is about 10, and this larger scale plant is assumed to be 3 plants in the BREC region in this case study. We can go to the next page. So we come back to this map showing the BREC region, and then you have the blue areas marked in this map, and that is the smaller plants, the distribution of them. It was about 10 of them in the blue marked areas in the map. And the larger 100 gigawatt hours is situated in the yellow marked areas in this map. We go to the next page. So some results from this study. Could say that approximately we have then used approximately 1/3 of identified biomasses. Some is a little bit more and some is a little bit less. And assumed to use it in a biorefinery concept. And then from those biomasses, 900 gigawatt hour biogas could be produced, and that is approximately 3 times the production of biogas today. And the biogas production today is mainly from waste and from sewage sludge. The hotel plant could then, from the fibers extracted from all those 13 biogas plants, generate approximately 130 gigawatt-hour of biofuels. And that fuels can be used for diesel and auto engines. But as I said before, the fibers extracted from the biogas plant is just a small share of the total feedstock that this hotel plant probably will use. Most of the feedstock will probably come from the forest. The system can also be self-sufficient of protein feed in the BREC region. And then with that, I mean that we don't have to import soy protein any longer. There's enough of methane production or biogas production. It's big enough for replacing natural gas in producing the mineral nitrogen fertilizer that the BREC region use. The region also have to start cultivate ley approximately at approximately 20,000 hectares to produce the feedstock that the biorefinery needs. And I showed the figure before that today about 200,000 hectares of arable land in the BREC region is used for cereal production to compare with, and the 28,000 hectares today in fallow. So this ley cultivation will not have any big impact in the production of food from this region, I would say. And with the system, with the production of ley cultivation, it will keep the content, the soil content in arable land where we have crop farming, although those farms also deliver straw to the biorefinery. And the reason for that is that ley is improving the soil content in the arable land. So the agriculture in the BREC region can be independent of fossil energy. And replacing the fossil energy in the system, that means that the reduction of climate gases will be approximately 0.3 tons of carbon dioxide per megawatt hour of produced biogas. The system can also redistribute phosphorus between farms and reduce farms that today, in farms where you have livestock production, you often have a surplus of phosphorus, and that could be redistributed to farms that have crop production. And by this system, you can reduce the total need of phosphorus with approximately 20% in the BREC region. Next page, please. So the production of renewable energy in the terms of it's larger than the use of fossil energy today in the BREC region. So the renewable production would be a little bit higher than 1,000 gigawatt hour per year, and the fossil energy use today in the BREC region is approximately a little bit more than 800 gigawatt hour per year. But you can say that the production of renewables with equal properties, with similar properties to diesel is not large enough. So you have to have strategies for that of course, and one is of course to replace diesel powered tractors with gas powered ones, and you have a picture of a gas powered biogas powered tractor on the picture here. It's from the farm Hagelsrum, and it used compressed biogas. But of course, you can also convert biogas to diesel by Fischer-Tropsch technology. We have not been looking at those kind of technologies in this case study, but it's possible. The reduction of greenhouse gases emissions are, as I said before, approximately 0.3 tons carbon dioxide per megawatt hour of biogas. But it can be larger if with supplementary technologies such as BioCCS, CCU, carbon capture storage or carbon capture utilization, with separated carbon dioxide from the biogas. When you upgrade biogas, you separate away the carbon dioxide. And some of the separation technologies generate more or less a pure stream of carbon dioxide, and that could of course be used for BioCCS. But you could also include and to apply technology into the concept, both to increase amount of nitrogen and use electricity for that in the dig state, but it also reduces emissions of methane, and that will also reduce emission of greenhouse gases. And if you included those two extra processes into the system, the reduction of greenhouse emission, additional reduction of greenhouse emission can be up to approximately 0.2 tons carbon dioxide per megawatt hour of biogas. And finally, Sweden we don't have any production of nitrogen fertilizers in Sweden. So, and further on, we don't have any natural gas grid. Or more correct, we have a gas grid, but it just covers a small part of Sweden. So if biogas going to be used in existing production plant for nitrogen fertilizer production, then I guess you have to liquefy the methane, biomethane generated at the biogas plant and transport it to production plant for nitrogen fertilizer. Okay, that was that. Thank you.
Mats, thank you very much. We appreciate your time and effort in delivering this presentation. And here comes the questions. How the system affects soil biodiversity, organic food for soil biota?
Okay, I guess it will improve the diversity, but also the carbon content. The reason why we included a ley in this system was to keep the carbon content in the soil at the farms producing crops. But of course, in those crop farms, they generally produce mostly cereals, but also maybe oilseed. And I think it would be good for those farms to include also ley in their crop rotation. Then they have a better variation in the crop rotation. But this is not my field, really.
Gunnar, your microphone is muted.
Yes, the next question. Thank you, Mats. With the old one smaller plant, why is over half the inside lay 16 tons sent directly to digestion instead of protein extraction first?
It's a good question. It was also a little bit the reason for adding lay directly into the digester without protein extraction was that we needed a certain amount of lay to cover the carbon losses at farms producing or crop producing farms that also were delivering straw to the biorefinery, and the way to cover the carbon losses by the exported straw was to cultivate later. So I think that was one of the reasons. Okay.
That was a good answer as well. So, to my knowledge, I think I hope we have covered all the questions for now. Yeah, Mats, well done. Thank you very much.
Thank you.
Thank you, and we are ready to move forward. We'll transition to the next segment. Our second topic for today, Pilot-SBG, Bioresources and Hydrogen to Methane as Fuel. Selin Anis from Germany. The German Biomass Research Center conducts application-oriented research and development in the field of energetic and integrated material use of renewable raw materials in the bioeconomy. So, Selina, you're welcome to speak.
Thank you for the introduction. So I would like to introduce you to our project Pilot-SBG. So in this project, we want to use bioresources and hydrogen to create methane as a fuel for heavy-duty transport or for ship transport. So I'll start right off with, well, our project and the background. So bioresources and hydrogen to methane. How does it work? Well, the bioresource that we use is biogas, but of course it has to be a cleaned biogas. And biogas can come from different, sorry, I tried to, don't know if you see this. Okay. Can come from different bioresources. And here we look into two different scenarios where we want to use waste biomass. So one scenario is agrarian biomass. So here we want to use cow manure and straw. So for the first half of the project, we will only look into this agrarian biomass. And then our second scenario that we will look into is making biogas from urban biomass like bio-waste or green waste. And maybe not every one of you is familiar with biogas, I'm not sure, so I thought I'd give you a small excursus on biogas and what it is like to work with biogas. So biogas is produced through the fermentation or anaerobic digestion of biomass, and it consists of different macromolecules, so proteins, lipids, and carbohydrates in general. And during the fermentation process, these macromolecules are getting smaller and smaller, so they're decomposed, and part of the biomass is, turns into a gas, mainly composed of methane and carbon dioxide. But then, of course, there's a solid residue, the digestate, that we also heard about in the first presentation. So when we only look at the gaseous product of this anaerobic fermentation, we get the biogas, and it contains methane in concentrations of 40 to 75 volume percent and carbon dioxide in 25 to 60 volume percent in general. But then, of course, there are traces. So the rest, which is not composed of methane and carbon dioxide, are trace components. And these can be a lot of different molecules. So the most important ones for our work are catalyst poisons, because we want to remove these catalyst poisons. There are still a lot of sulfur-containing molecules from amino acids in the biogas, in the biomass. There's ammonia, and there can be siloxanes if we use urban biomass, for example. And these are traces that we need to remove. So I told you before, we need to use cleaned biogas. So we want to clean the biogas from these compounds. All right. Another goal by using the biogas is to increase the methane content. We can have up to half of CO2 in the biogas. So one way is to remove or separate the carbon dioxide by separating methane and carbon dioxide. But another way to, well, increase the methane content is to use the carbon dioxide, for example, in a methanation. So this is kind of the reaction that I already showed you in the first slide, but we look into this again. So I'm a chemist, my background is chemistry, so I like chemical reactions like this one. So you see, we still work with the cleaned biogas. So in our input, we have methane and carbon dioxide together. But when we add hydrogen, the carbon dioxide and hydrogen can also react to methane, and water is also a byproduct. So this reaction is exothermic, which means that during the reaction, heat is produced. And now you might wonder, why do we want methane as a product? Well, first of all, we have methane in our biogas, and you see we have two parts of methane as an output in this reaction. So one is the methane from biogas, so this doesn't react. But then we also have a part of methane, which is from the reaction of carbon dioxide and hydrogen. And methane is a really interesting molecule. It can be very versatile, so we can use it as a fuel. This is what we make it for. And well, the one thing with working with biogas is that we already have the methane in here. So it makes sense to use the carbon dioxide, the carbon that's also in here, but without an energetic value, and then make it more valuable by transforming it to methane. But well, methane is not only a fuel. In general, it's an energy carrier, as you might know, of course. And its volumetric energy density is 3 times higher than the one of hydrogen. So it also makes sense to use hydrogen to make methane. Methane is also used for high temperature generation, which works really well. So if we have a process where we need high temperatures of 1000 degrees Celsius or more, we need methane. Then, as I said, methane is also a very good fuel, and it causes low CO2 emissions. And methane can also be used as a precursor for chemical industry. So I just want to highlight 2 more things here. So the energy carrier is because we have a very high binding energy of carbon to hydrogen in alkanes, but it decreases with the size of carbon atoms in alkanes. So if we look at this diagram for methane, we have a high binding energy of carbon to carbon-hydrogen bond of 435 kilojoule per mole. So we have 4 of these bonds in one methane molecule. And for butane, it already decreases to 389 per carbon-hydrogen bond. So if we consider this and look at the size of the molecule, then we see that methane, well, smallest molecule, has the highest binding energy of each bond. So this is why it's such a good energy carrier. And the second one, I want to explain why it is a fuel with low carbon dioxide emissions. For that, we need to look at the carbon to hydrogen ratio of the different alkanes. This is here. So in methane, we have 1 carbon per 4 hydrogen atoms in the molecule. And well, for the other alkanes, we have more hydrogen per carbon. Well, yeah, so the carbon to hydrogen ratio is the lowest for methane, and low carbon means low carbon dioxide emissions. So this is actually a quite good fuel compared to other fuels that are used in the transport sector. All right, moving on to our pilot plant. So I wanted to introduce you to our project Pilot-SBG. So Pilot-SBG stands for Pilot Plant for Synthesized Biogas. And this pilot plant that you see here is located in Leipzig, Germany, where the German Biomass Research Center is. Well, here you see some of our processes. So this is the anaerobic digestion. One part is here, the other part is here. Then there's a hydrothermal treatment, methanation here, but it's hard to see. So I have a little sketch showing the 4 main processes that are happening in this plant. So in the photo, we were looking from here down here. We could see part of the methanation, anaerobic digestion, HTP, hydrothermal process, treatment here. And then the 4th process is the digested processing. But so you can understand more what we're doing exactly in this pilot plant, I have a little flow sheet or the process chain of the whole pilot plant. And of course, the hard process is the anaerobic digestion. So here the biomass is fermented. And as I already told you, as biomass input, we have these 2 different scenarios. So one is with agrarian residues and the other one is with urban residues. And as I said, for the first half of the project, we will only work with agrarian residues. And once we've done enough research on this biomass input, we will move on to the urban residues. So these are 2 different scenarios. Then the biomass can go into pre-treatment, but this is also a research question if pre-treatment increases the methane output in the biogas. So sometimes we will do anaerobic digestion with pre-treated biomass, but then we also look into untreated biomass. And then in the anaerobic digestion, we get biogas, and we continue working with biogas in the catalytic methanation, and we get the digested, and here we continue working in the digested treatment. So with the digested, we can get different products. So our main products here are hydrochar from the hydrothermal treatment, a fertilizer from the digested treatment, and we also get processed water here that we can use in other processes in the pilot plant, like in the fermenters, so we can recycle the water. Then with the biogas, as I said, first of all, the biogas has to be cleaned, and afterwards it can go into the catalytic methanation. So here we need hydrogen, and then the biogas can be transformed to renewable methane as compressed natural gas. And then outside the scope of the pilot plant, but this will be an addition, is that we liquefy the renewable methane into LNG, and this will be the biofuel that could be used for heavy-duty transport or for ship transportation. All right, so in this pilot plant, we have some highlights that I want to show you in the next slides. And again, we will start with the anaerobic digestion. So as I said, we start with biomass in this process, and we have 2 different reactor lines in the anaerobic digestion. So these consist of 3 reactors each. So the first one is the main reactor, and the second and third ones are post-fermenters. And both lines, so the difference between them is the first main reactor. So in the upper one, there's a plug flow reactor. So usually this is used in agriculture. And in the lower one that you see here, we use a stirred tank reactor. This is commonly used in treatment of organic waste. But as I said, first of all, we look into the agricultural biomass, but we will use the agricultural biomass in both reactors, and so we can get a comparison of these 2 reactor concepts. So our outputs in this anaerobic digestion module will be biogas and the digestate. And as I showed you before, we continue working with both of these products. So next up is the hydrothermal treatment. So this can be used as pre-treatment or upgrading. And we have a really big reactor here. So this reactor is 500 liters, and it's quite big. So this almost goes up to the wall of the pilot plant. And here we can either use biomass and treat the biomass, or we can use the digestate and make product from the digestate. So this hydrothermal process reactor works with temperatures up to 240 degrees Celsius and pressures up to 40 bar. And if we use it for the biomass pre-treatment, of course, we want to make it better accessible for the next step. So we use this for difficult to access biomasses. And here a lower temperature and lower residence time is used in the reactor. Whereas if we use the hydrothermal treatment for the digestate treatment, we will use higher temperatures and higher residence time. And here the product will be a hydrocarbon or hydrochar. And this can be used for gasification. And in gasification, we could get a synthesis gas. We could make other products, for example, with Fischer-Tropsch synthesis, or the hydrocarbon could also be used for carbon capture and storage, like in soil incorporation. Right, the third process is the digestate treatment. So the digestate could either go into the hydrothermal treatment or into this digestate treatment. This mainly consists out of 2 steps. So the first step is a solid liquid separation, because the digestate is still quite liquid. There's still a lot of water in there. So we have 3 processes that work here: a chamber filter press, a press screw separator, and a decanter centrifuge. And then a second step for further treatment, or here in this treatment, for example, we get a liquid fertilizer. So this fertilizer could be more concentrated in this liquid phase concentration with an ultrafiltration. And this is also the step where we would get the water. So our output here is a solid organic fertilizer, which is rich in nitrogen and phosphorus. So this is obtained in this solid liquid separation step. Then the second product is an inorganic fertilizer. This is liquid and high in nitrogen and potassium. And then also water is the third product here. And the fourth process is the catalytic methanation. As I said, here we work with biogas. And here we basically have 3 steps. So first step is the biogas cleaning. Here we use 2 really big adsorption reactors. They're quite oversized, so we make sure that all of the catalyst poisons are removed. Then the second step is the methanation in a methanation reactor. And here we use transition metal catalysts. So here we don't want any sulfur or any other catalyst poisons entering the reactor. This is why we have this biogas cleaning in advance. And the third step is CO2 removal. We do this with the sodium hydroxide scrubber. It's not presented here, but still it's an important step, because there can still be unreacted carbon dioxide in our product. And then the output that we get here is the biomethane, which is the main product of this process. So this is supposed to be used as a fuel in the end. All right, so the catalytic methanation is something that I work with, so I can give you some more insights on our experiments that we've been performed so far. So I started with small-scale testing before moving on to the pilot plant. And here in the lab, I have a fixed bed reactor, which has a volume of 64 milliliters. And it can operate at up to 8 bars at different temperatures, different gas hourly space velocities. And in the lab scale, I have a gas mixing station where I mix methane, carbon dioxide, and hydrogen, or for specific experiments, also hydrogen sulfide to test poisoning on the catalyst. So the differences to the pilot scale are that in the pilot scale, we have a bigger reactor of 560 milliliters, and we can go up to 20 bar. So higher pressure is better for the methanation reaction. And also in the pilot plant, we can use real biogas. We can also mix biogas from technical gases, but we have the opportunity to use the biogas from the anaerobic digestion. And the other factors are either the same or really variable compared to the small-scale testing. So in the small-scale testing, I was looking for 3 easy-to-change parameters for a design of experiments approach to find the best parameter combination for my catalyst in the pilot plant. So one factor is the temperature that's easy to change, the gas hourly space velocity. And the third factor is the hydrogen to carbon dioxide ratio, which can also be adjusted. And so you see the design space here. So each dot stands for one experiment that was performed in the lab scale, and the center point was performed 4 times, the black ones 2 times in the smaller scale. So looking at the results, I tested 6 different catalysts. They're based on nickel or ruthenium, on alumina or cerium dioxide. These are support materials, and these are the active materials. And well, if we look at the parameter combinations, in general, we see that the catalysts on alumina, they work better at higher temperatures, but they need rather low hydrogen to carbon dioxide ratios. So it's down here or in the middle. And for the gas hourly space velocity, they rather need low ones. And for the analog catalysts on the other support material, on cerium dioxide, these work better at lower temperatures, but then the hydrogen to carbon dioxide ratio should also be rather low or in the medium range. And the gas hourly space velocity is rather it can be different here. So when we do tests for biogas methanation, it's important that the hydrogen content in our product gas is lower than 2 volume% if we want to use it as a fuel. And here in the diagram, you see the product gas contents of methane in green, hydrogen in blue, and carbon dioxide in gray. And if we look at the blue bars for the hydrogen, we see that 2 catalysts are above the 2 volume%, which is the limit for using methane as a fuel. So this should be decreased, but for these 2 catalysts, this was the best result. So it seems like these 2 catalysts don't work well for the pilot plant. However, in the pilot plant, we can use higher pressure. So I thought we should make a prediction for the catalyst performance in the pilot scale. So I performed an Aspen simulation with the best parameter combination that I found in my experiments. And I did the simulation for 20 bar. And we also have a bit of a different condensation situation in the pilot plant. So might look like the methane concentration decreases, but there's only a bit more water in this product gas, which is not depicted here. So the methane concentration is still high. But if we look at the hydrogen again, we see that only one catalyst really isn't suitable for the pilot plant. But this one also works. It goes below 2 volume% of hydrogen when we go up with the pressure. So I decided to continue my work with these catalysts. And the second experiment I did was catalyst poisoning with hydrogen sulfide with 500 ppm hydrogen sulfide in the gas stream. So in this diagram, you see the time in minutes on the X scale and the catalyst on the Y scale. And this is the time it takes for the catalyst to completely deactivate. So the longer, the better, because we don't want the catalyst to deactivate. So if we look at this, we see that 2 catalysts are much better than the others. So these are the 2 catalysts with nickel. It takes 28 hours or 50 hours for the catalyst to deactivate with 500 ppm hydrogen sulfide in the gas stream. So for the pilot plant, this means that I expect a rather low poisoning effect because the hydrogen sulfide concentration of 500 ppm is really high. So we don't expect these high concentrations in the pilot plant. We rather expect maybe 1 to 10 ppm hydrogen sulfide max. So yeah, it should take much longer for the catalyst to deactivate in the pilot plant. And also we will have a much higher catalyst volume. So more catalyst takes more time to deactivate. So I think this effect will be low in the pilot plant. All right, a quick outlook on what we're doing in the pilot plant right now. So we're still in, well, commissioning the plant right now. This is, by the way, the methanation module. And once we're done commissioning the plant, we will start experiments with the 2 nickel catalysts that I just showed you in the poisoning experiments in this methanation reactor here. And then these are 2 adsorber units, and the materials that we use in here and the catalyst, both of them will be, we will do an environmental and economic assessment for catalysts and adsorbents. Yes, and in the end, I wanted to go back to the topic of circular bioeconomy of this webinar series and wanted to show you how our pilot plant contributes to circular bioeconomy. So, well, our main product is a biofuel. So the biofuel should be used in some kind of transport. So when the biofuel is used and burned, of course, it will lead to carbon dioxide emissions. But this carbon dioxide emission will be taken up by biomass. And biomass is what we use in our pilot plant again. So it's kind of a circle, and we don't add more carbon dioxide emissions as we would do if we use fossil fuels. So I think it makes a lot of sense to make fuels from biomass. And then also internally in the plant, we have like small recycles like water recycle. And also we try to make a lot of different products from the biomass, like the fertilizers. So this is how we try to contribute to the circular bioeconomy. And last but not least, I would like to show you that we already worked on some really nice booklets. So if you're interested to learn more about methanation, we have this booklet on methanation. We have two more. So one is on a market analysis in greenhouse gas quota for renewable methane in transportation. So if you're interested in more numbers. And the third one is on infrastructure for renewable methane in transport. So feel free to download these booklets. They're for free, but so far they're only available in German, but we're planning to also translate them into English. So maybe sometime they will also be available in English. Yeah, if you have any questions, feel free to ask me now or send me an email, or you can always check out our project website. This is also available in English, so you will find more information there as well. Thank you very much.
Selina, thank you. We are grateful for your very informative presentation. And we have a question, actually. How many gigawatts stays in methane from 10 gigawatts of electric energy produced in wind park? Yeah.
Okay, sorry, I don't really have an answer for these
Very specific number. You are asked to answer specific numbers. How many gigawatts stays in methane from 10 gigawatts of electric energy produced in wind park? This is a question.
Yes, I see the question in the chat. But so for this number, I don't have an answer, to be honest. I can tell you that we produce 2.5 cubic meters of biogas per day. So this is what we do. But yeah, no, sorry, I don't know how to answer this right now.
Okay. For now, it's okay. And one more question. How do you see the future development and adoption of biogas or biofuels, particularly in the context of renewable energy transition goals? Is it going to be economically affordable and beneficial?
Okay, so I think like once we have this process and we have the possibility to scale up this process, there will be room for optimization. And I think, of course, like after some time, after optimizing this process, it makes sense to have such a process. But of course, it won't be used like for cars, for personal transportation. This will go rather towards electricity, I think. But for heavy duty transportation, which is hard to electrify, I think these kind of processes really make sense. And yes, I hope that like once we have the possibility to scale up these processes and optimize them more, that they will be, well, they will find their place in the market.
Selina, thank you again. And if there are no further questions, we can move forward to the next presentation. So welcome Adelina Stuparu, a region Västra Götaland, Sweden. And the topic, BREC Lesson Plan on Circular Bioeconomy Technologies, material for teachers and lecturers. Finally, we have come straight to the teachers. Adelina, you're welcome to speak. Adelina works in close collaboration with upper secondary and adult and higher vocational education department. Adelina, floor is yours.
Thank you so much. Yes, indeed, I work for the Nature Resource Department, and in my organization, we have 2 mandates from the Västra Götaland region, which also Matt talked about a little bit earlier. And the first one is to manage vocational education schools. And the second one is to work with development and innovation in the green sector. So this is perhaps a little bit, this is maybe not so common, but we use our schools as test environments for development and innovation projects. And we work in close collaboration with universities and researchers and businesses, anyone who wants to come and test things with us. So in that sense, in the BREC project, we have 2 main goals, I would say. And the first one is to find the best strategies to transition to a circular bioeconomy in the regions within the project, but also outside. And then the second main goal is what I'm going to talk about, which is transferring this knowledge from the researchers to the students. And I would like to start a little bit with why we are doing this lesson plan, because I was asked that question. I was at the conference and someone asked me, why would you do that? There are so many materials out there on the internet and everywhere. You can literally just pick something that someone else did. And I agree with that, because during this project, I think we have all learned that the internet and also within our circles, we can find a lot of information. But despite that, this information doesn't quite reach the students who will become the future farmers. So if we think that we work with the green sector, they are young and full of energy and creative, and they want to be part of a transition, but this information doesn't quite get to them, or not so easily. Of course, they learn about renewable energies and things like this, but not so much about the bigger picture and the whys. So what we did in order to do that, to make sure that this information and this knowledge is transferred, was to establish a teacher reference group, because we thought like this: the teachers are the main actors, the people who are going to help us transfer this knowledge. And yet when they went to university years and years ago, they didn't learn about these topics. So they require constant competence development in order to keep track and to feel secure in what they are going to teach to the students. So we established this reference group, and we have members from Finland, Sweden, Latvia, Norway, and Germany. So we gather all of the regions in the project. And we have both, we have, for example, upper secondary teachers, and we have higher vocational education teachers. We also have people who are not directly teaching in a classroom, but are still connected to students and can transfer this information, which was really good for us, because we have diversity in terms of geography, but we also have diversity in terms of skills and backgrounds. And I myself am not an expert in this topic, and I'm also not a teacher, but mostly a facilitator. So we all contribute in some way. So first, we organized a competence development webinar with our researchers, and we invited all of our teachers to participate to talk about a sustainable transition and how it would look like. And then the second part of this competence development journey was to organize a study visit to Finland. And there we visited our partners from Luke. And we went into this biogas plant, and the people there were so kind and lovely, and they took us to every step in the process. So whatever we wanted to know, and we had so many questions as well, and they were patient with us and answered everything. And from how they procure the biomass and the input to the various processes, and how they produce the heating, the electricity, the collaboration with the farmers, the nutrient recycling, how they work at the different stages. So it was a very good, a very important part in our journey. And then we decided like this in order to structure this and not think, okay, there's so much out there, what are we going to focus on? We actually decided to create learning goals. So this had to be in some way structured. So we have a base of knowledge that we want to use in the project and that we want to transfer in the project, but we also wanted to have a flexible format because we think this is important not just for, say, agriculture students, but what they do is if we just take the agriculture part, then we are limited ourselves because we can talk about these topics in civics. We can talk about policy. We can talk about the future direction. We can talk about it in entrepreneurship and to help them develop their creative ideas or agricultural machines. So it can be, we wanted it to be flexible in that way. And then first, when we looked at the lesson goals, we looked at what do we want the students to know at the end of this lesson. And then, of course, it's not just about knowledge, but also what we want them to be able to do. So this was the first step in making that. It was very fun and very visual. We gathered together and we made this tree to have, and we've been using this tree quite a lot, so it was a useful tool. And in the bottom, at the roots of the tree, we have the knowledge that we want to give to the students. And to say just in this early stage, when we made the tree, there was a lot of focus on biogas, and we have expanded a little bit as well, because we think everything can get better all the time. So the knowledge at the bottom, in the trunk of the tree, we talked about understanding. What deeper understanding do we want them to acquire? And then in the crown of the tree, then we thought about abilities. So for example, assess what raw materials can be utilized, or simply outline a biogas process and all of the biogas plant. We can start with a simple one, for example, if we're talking about 16 to 19-year-olds, or it can get perhaps a little bit more complicated for the higher vocational education students that would have a bit more knowledge that they bring with them into the lesson. We then moved on to developing the content, and we wanted the teachers that we will disseminate this to have quite a lot of information, and then also to have easier tools that can be ready-made and easily adaptable here and there. So based on the webinars that we took part in, we also acquired some textbooks from Germany, thanks to our German participant who gave us a tip. And also based on the visit that we did, we started to develop the content. And we decided to have it like this, an ebook format where the teachers can go to and they can consult basically absolutely everything. And this is for them to have the security that, okay, I can go more in depth. I don't just have like one PowerPoint presentation, and then if I get asked questions, I won't know how to answer them. And then, yeah, the second point would be to have some ready-made presentations that can be given to the students. I have a bit of information about the contents of both the ebook and the PowerPoint presentations. And I have to say that I do not have finished material to show you because right now we are just doing the input of all of this content into our tools, into our visual tools, the book and the presentations. But we started, we thought it would make more sense to structure everything in this way. First, we are looking at the basics of the bioeconomy. We look at terminology, and we have a list with all of the terms at the very beginning. We look at what is different between the linear and the circular bioeconomy. And then we also present the nutrient cycle. We go on to talk about technologies and challenges. We will address resource management. So how does agriculture, forestry, and aquaculture fit into this bigger picture? And we will present also general principles of biorefining. And one thing we wanted to show is this cascade of all of the inputs and outputs, and it can get quite big, but perhaps for the students, not as big as the one that Mats showed. When we look at technologies, we discussed a selection, biogas production, how we produce energy, electricity, and heat, fertilizers, pyrolysis, gasification, protein extractions, among them. And of course, it's not really so good without giving some practical examples. So we will involve case studies and scenarios. And we thought it was also very important to describe how all of these activities are connected with all of the machines on the farm. And I think this would be quite important because in our experience, students are very excited about all of the machines and the vehicles. So that would be also important. And I think I met the last part of my presentation already. Here we will talk about implementations and solutions. So we will look at the challenges, of course, because we want to be realistic. We will also look at the strategies that are most sustainable right now, or are also deemed to be sustainable for the future. And as I mentioned, it can fit in so many different courses. So we also look at policy. How does this feel with the plan for the next, for example, until 2030 or 2050? So we're going to look at very briefly the EU Green Deal, global policy, and even where it fits regional policy. What does this mean for in terms of environmental impact? Why is it beneficial? And I think we all can agree that this has a good impact on the environment, especially when we think about the comparison with the conventional agriculture that has dominated society for so many years. And then more possibilities. We also looked into different products to give examples. What exactly can come out of this process? So we can have protein feed, for example, or we can develop textiles or fibers, bioplastics. And we can also look into the fact that having a biorefinery can lead to pharmaceutical ingredients, for example. So like there are many ways to sort of show that this is not just a matter of like, we're not just talking, okay, we're going to produce some electricity, but that there are implications for so many industries and so many sectors. Yes, I was efficient. And that was it from me. There's a lot to do, I feel, in our field of work, and we need to be very efficient. So I think I brought that with me in the presentation.
Great, Adelina. Thank you very much. Thanks for sharing your experience, very important work with us. And we have a question actually. How is acceptance among students for circular agriculture?
I would say it's good enough, but I would say that also that we don't talk a lot about the why this is important. So this needs to be present in more perspectives, in more courses. For example, why this is important for society and for students to get a much bigger picture. And if we think about the curriculums, one thing that we are challenged with is that they are very much a box. So it's very hard to get outside of that box. When I spoke to I mean, I don't have so much direct contact as the teachers have, but when I do speak to them, they say this is very important for us, and that is being more sustainable and having a more sustainable society. But if we go into the details of how this will be done, it's not so easy to say, yeah, I would like the whole world to have biorefineries and to produce biogas in agriculture, because that's very important. I hope that answers it. So I'm not so directly connected, but I do think that it is important for the students to transition.
Thank you. And one more question about teachers reference group. You mentioned about different backgrounds of these teachers, but how did you select them? How did you find them?
So at around the time when the project was starting, and it was October 2022, we made a document. So we presented the project and then our goals and what we wanted to do. And then in a little bit more details, the specific goals for group of activities 2, which is what we're dealing with, developing a lesson plan, and then what the requirements were. So for example, attending several hours of webinars, contributing to content development. So when that was ready, it was almost like a job advertisement announcement. But we were very clear that it wouldn't entail so much work, just coming in at the various stages. And then we disseminated it with through our partners. We also posted it, the announcement on our INTERREG Baltic Sea website, and LinkedIn, and shared it in the usual ways.
Okay. And one more question I've got, when will this study material be available and where will it be published?
It will be available in O2. So right now we are just filling all of these contents into the PowerPoint presentations and into the ebook. And then what we will do, the next step, is also to translate it. So we will have a translated version for each region. This should be finished just before the summer break. And then it will be ready to publish. And where it would be published is not yet ready, because it has to be available for a really long time. So we started considering adding it to the project website, but this has a deadline or like a time limit, or also on our respective websites, but it would be shared very widely. And if I would say we can probably share it even with the participants in these webinars.
It's very good. Amalia,
Yeah.
Adeline, thank you very much. Thank you very much. Thank you all for your questions as well. As I see, there are no more questions for now, so we will now proceed to the next agenda item. Thank you, Adeline. Thank you very much. And now here comes the interactive feedback survey as it goes. So, Amalia, are you ready to speak?
Yes.
Welcome.
Thank you.
You're welcome to speak.
So I will send in the chat how to access the interactive feedback survey. I assume most of you have done it once or twice before already. So this would be the last one. Access menti.com either all on your smartphone or in your web browser, and use the code 4937622. And then I will share my screen and start the survey. Okay, so this interactive feedback survey is for our info material that we have developed. It's to get some feedback on what you think we should work more on, or what you think we should focus on. And the first question I have for you is what target group you represent. I'll give you a couple of minutes to answer that. Great. So it seems like most of you put your answer in. Yeah, one more there. Seems like the research institute people are the most of the audience is from the research institutes. Okay, so I think we will move on for now. So question 2, building on today's webinar, what would you be interested in learning more about? And here you can put some words and we will make a word cloud, so to say. We'll give you a few minutes on that as well. So we have cost efficiency, we have biorefinery, ultrafiltration, combined technologies, biomethane. Catalytic methanation, we have nutrient recovery. It's a lot of good words here. Scale up, biochemical methanation. Okay, I think that would be most of the responders. Is there any more words you would like to put in? You have to put them in the next 10 seconds. Okay, so I will move on to show you our draft to this info material. And we have chosen circular phosphorus practices as an example. This will be like info material, easygoing way explaining how what phosphorus is and how it's or why it's important to have circular practices. And the first thing we focus on is what phosphorus is and why it is such a vital resource. And also that there are some challenges that we need to cope with phosphorus. So that will be the first page of our info brochure. And the second one is the phosphorus cycle. And we tried to, with this picture, illustrate the cycle of phosphorus and how it moves through soil, water, and living organisms, and how it's playing this vital role for plant growth. So this is also to illustrate how phosphorus is such a circular nutrient and why it's important to circularize it. and it's supposed to be easygoing and easy to understand for everyone. And then we present the challenges. We have here focused on 3 different challenges. It's food security, eutrophication, and inefficient use. And in food security, we focus mainly on how phosphorus reserves are in geopolitical unstable places like West Sahara and China and Morocco. And for eutrophication, we focus on the vast use of virgin phosphorus and how over fertilization can lead to leakage into water reserves and impact the biodiversity in the waters. And for inefficient use, we talk mainly about this linear use of phosphorus and how it ends up as waste, for example, in the agriculture and also in the aquaculture with the fish farming. And then as a solution, this is just an example, but we used struvite extraction as an example of solutions to the circular phosphorus practices. And here we present briefly what it is, and we also briefly present what is the benefits of using struvite extraction. Yeah. So here we focused on resource recovery, prevention of scale formation, environmental protection, and the cost savings. So this is the draft of our info material. And then I would like you to answer a couple of questions related to this. So the first question to this one is to rank these statements from strongly agree to strongly disagree, to whether you find the information insightful, easy to understand. Yeah, you can see all the questions. I will give you a couple of minutes to answer these ones. You can just like pull on the bars depending on how much you agree or disagree. So we have 10 responses. Is there still a few more we are waiting for? Okay, I think that will be it. So I will move on to the last question. How would you rank the importance of the following type of information when comparing bio-based technologies? And here you can just pull the answers to what place you think they deserve. Yeah, so I will give you a couple of minutes on that as well. Okay, so I think we are getting close to all the responses. I will stop the slide sharing, but you should still be able to put in your answers. So, okay, I would say that that will be it for me and the survey. And I will also like to just spend the opportunity to thank everyone for responding and for INTERREG for funding our projects. And also, of course, for all the listeners. And with that, I will give the word to Inga and Gundars to end up the webinar.
Yeah, Amalie, thank you very much. Thank you very much for your job. And actually, I would like to thank you, Inga, as well, and all the team, Ujis, Ariana, Selma as well, all the team members who brought us all together across 6 countries, actually, for this webinar. And
Yeah.
Inga, do you have, my co-host, do you have any closing words, remarks to say?
Yeah, I just wanted to say the greatest and many thanks to all the presenters who devoted their time to share their knowledge. And I think we have made this event together, and we have recorded it, and also in BREC's webpage these recordings will be available if somebody would like to just remind some knowledge. We will send the link shortly after this, where these recordings will be available. Thank you and have a great day.
Good. These recordings will be available after about a week.
Yes.
And yeah, so hereby we complete the 3rd webinar, Technology is Paving the Way to the Circular Bioeconomy. I would like to say thank you very much and actually have a wonderful day.
Thank you, everyone.
Bye.
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 Thank you.